Now let's turn to the top of page 19 and let's talk about shifting equilibrium. Because once the system has reached equilibrium, you could add components or remove components. You could change the pressure or the temperature to shift the equilibrium point. That is to bring it to a new equilibrium point where the relative quantities have changed, all right, the relative amounts. All right, so the first thing we should do is first state the rules, and then we'll apply these rules to some examples. All right, so the rules of shifting. You might recall this under the title Le Chatelier's, I think I pronounced it right, his principle, which Le Chatelier said that when a stress is applied to a system of equilibrium, the equilibrium will shift in the direction that relieves that stress. Or simply put, whatever you do, it tries to undo. But I find that a lot of students find this confusing, so the rules of shifting will certainly help you. So the equilibrium will shift in the direction away from the component that is added. See, what you do tries to undo, tries to use up whatever was added. And the equilibrium will shift in the direction towards the component that is removed. We'll see how that applies in a second. Then, as far as the effect of this shift, once you've decided that the equilibrium shifts to the right or the left, let's interpret what that means. All right? A shift to the right causes everything on the right side to increase and everything on the left side to decrease in concentration or amounts, depending on how they ask the question. And a shift to the left causes everything on the left side to increase, while everything on the right side decreases. We'll see more of that in a second. Then, as far as temperature is concerned, whenever they mention an increase or decrease in temperature, I want you to translate that to an increase in temperature as adding heat, and a decrease in temperature as removing heat. And remember, the heat is going to appear as kilojoules, typically in an equation. So when you increase, you're adding heat, and when you decrease, you're removing heat. And then for pressure, because pressure can also shift the equilibrium point, an increase in pressure will shift the equilibrium towards the side with less moles of gas. You're going to have to count how many moles there are by the coefficients in the equation. And a decrease in pressure shifts the equilibrium towards the side with more moles of gas. And finally, before we begin applying these rules, just watch out for the things that don't shift equilibrium. And that is catalysts, solids, and liquids don't shift equilibrium. So everything remains the same when you add these. Catalysts will speed up the rate of both reactions equally, so you'll reach equilibrium faster with the catalyst, but that's about it. Now let's go to some examples of shifting that I have for you here. That's a pretty big grid there. Again, the principle, what you do, that will be the stress, it tries to undo, and that will be the shift direction and the results on the concentrations. So what we have here is the classic reversible reaction with nitrogen and hydrogen producing ammonia. Notice that there's heat being released, it's on the product side. Now we're told you adding N2, or in other words, you're increasing the concentration of N2 on the system. Well, if you add N2, since the N2 is on the left, it will shift away from the N2. Equilibrium shifts away from the component that is added to use it up. And since it shifts to the right, then that means everything that's on the right side, the NH3, will increase at the expense of what is on the left side. So in other words, to increase the amount of product, then you have to consume reactant. So the H2 decreases. Now let's try pressure. In order to predict the result of pressure, you have to count moles. So there's 2 moles of ammonia on the right, and there's 1 for N2 and 3 for H2 So there's 4 on the left. A decrease in pressure will shift the equilibrium towards the side with more moles of gas. So in this case, it's going to shift to the left. Shifting to the left means everything on the left side is going to increase. H2 is on the left, while everything on the right side will decrease. Decreasing temperature. Remember, you want to translate that into adding, or I should say, the decrease is removing kilojoules. So find out where the kilojoules are. Even though you're removing heat from the entire system, one reaction is affected more than another. In this case here, when you remove the heat, it's going to shift the equilibrium towards the component that's removed, treating heat like a component. And a shift to the right, once again, is going to decrease the H2 and increase the NH3. And again, catalysts, as I warned you before, don't let that fool you. Catalysts speed up reactions by decreasing activation energies, but the catalyst will not change the equilibrium point. So this is no effect, no shift, in other words. So this will remain the same, RTS, and this will remain the same, RTS. All right, why don't you try practicing the next grid. I call this an equilibrium grid or shifting grid. See how you do, and then I'll catch up to you. You could pause now if you like, or just follow along with me. Okay, so let's look at this reaction here. The first thing you want to note is the solid there, because that is a trap. Remember, solids, when adding and removing solids from a system that's reached equilibrium, doesn't do anything. So that's why this first question here, remove I2 solid. Because of solid, we get no shift. If there's no shift, then this remains the same. And so does this. Then increasing pressure. Well, if you're going to increase pressure, again, you're going to have to count moles of gas, and only gas, so don't be fooled by the solid again. So there's 1 mole on this side, and there's 2 on this side. There's 1 H2 here. So an increase in pressure will shift to the side where there's less moles of gas. In this reaction, that would be to the left, which means everything on the left side, the H2s on the left, will increase. Everything that's on the right side will decrease. Increasing temperature, let's translate that into adding kilojoules. Find where the kilojoules are, which is on the left side here. So if I add heat, it's going to shift away from the heat. So it's going to shift to the right to consume that heat, to undo what I just did. And so the H2 will decrease, and the HI will increase. And finally, if we increase volume, well, remember, volume and pressure are inversely related. So an increase in volume will decrease the pressure, that is the volume of the container. And so you're going to shift to the side with more moles of gas, which is to the right, which again means the H2 decreases and the HI increases. Okay, that's good for shifting. And if you think about it, that's 1, 2, 3, 4 by 1, 2, 3. That's 12 questions just in this grid that you did. So that's good practice. Now let's turn to the bottom of this page and finish up equilibrium with a discussion on, or notes on, better said, on the spontaneity of a reaction. So, a spontaneous reaction is a reaction that, once it gets started, it continues to react on its own. Like, for example, a piece of paper burning. Once you light it, once you've supplied it with its activation energy, that paper will continue to burn on its own, provided there's enough oxygen. All right, so that's a classic example of a spontaneous reaction. So it continues to react, its own. And you ought to know, to predict the spontaneity of a reaction, the two tendencies in nature. Nature favors lower energy, and nature favors higher entropy. Remember, low energy means an exothermic reaction. And don't confuse energy with entropy. Entropy is a measure of the disorder or randomness of a system. And there's a number of ways to follow or track entropy. Two ways you should know are A, when you look at the phase changes as you go from solid to liquid or aqueous to gas, entropy increases. There's more disorder, so nature favors that direction. And also, if you increase temperature, you increase entropy, since particles will have more kinetic energy at a higher temperature, more motion, more disorder. Now, if you put these two things together here, altogether, any reaction that has both 1 and 2, both a decrease in energy and an increase in entropy, which would be a reaction totally in line with nature, that reaction would be spontaneous at any temperature. I have here a diagram to help you remember that, about these two tendencies in nature, and that is the following. We have here an exothermic reaction, as you can tell. We end up lower than where we started, going from reactants to products. And we're going from the solid to gas, in the solid to gas direction. So, a release of energy and an increase in entropy. Easy way to remember that is nature is lazy. That means disordered. Lazy means lower in energy, and sloppy means disorder. So that might help you to remember that. Okay, so let's look at some questions now on kinetics and equilibrium. Or again, you could take a break, go through your notes one more time, and I'll catch up to you.